Okay, so you know that feeling, right, when you're learning some math thing, and it just feels like it should be way easier than it is.
Oh, yeah.
Like, it just won't click. And it feels like the first thing everyone does is like, oh, let's get out like a visual or a model,
Yeah,
right?
for sure, for
Like,
sure.
that's going to make it all better. Um, and whether it's like, actually getting out physical objects or drawing some kind of diagram, it's like we always reach for these models to make the abstract stuff understandable.
Definitely. Yeah, you see it everywhere. I mean, from like, the little kids in elementary school all the way up to like online courses and stuff.
Right.
The whole idea is to give people something concrete to grab onto,
Yeah,
as a starting point to figure out these math ideas.
totally. And that is exactly where we are diving in today. So we're not just looking at how these math models can help us learn, but we're going to explore a little bit of a twist here.
Okay.
When and why they might actually stop being so helpful or even become like a hindrance.
Interesting.
We're calling this the model breaking point.
Okay.
And for this deep dive, we're looking at some research from 2014 that looked at this phenomenon specifically.
Cool.
And we're going to be focusing on two really common examples. The first is the chip model that's used for integer subtraction.
Okay.
And the second is the area model, which is used for fraction addition.
Yeah, those are classics for sure.
Yeah, totally. And when we say mathematical model here, we should probably clarify what we mean.
Yeah.
Because our source defines it pretty broadly. It can be any kind of material or like visual sketches or situations or diagrams or even symbols
Wow.
that help us like wrap our heads around the math concept.
Okay.
But we're really specifically interested in what they call presented models.
Okay.
So that means like the ready-made tools that are shown to learners.
Gotcha. So like not models that the students are building themselves.
Exactly.
Or like, the broader idea of mathematical modeling that you might do like in a science class or something.
Exactly. So we're not talking about, building a model bridge using ratios or anything.
Right.
It's more like, the teacher pulls out colored chips to explain negative numbers.
Yeah, yeah.
Or draws a rectangle and cuts it up to show fractions.
For sure.
So that's our focus today. So what's in store for you in this deep dive?
Well, we're going to look at these really common teaching tools, and we're going to talk about why they're so popular, like what their strengths are.
Okay.
But then, more interestingly, we want to get to, like, where are their limits?
Interesting.
When do they actually stop being useful?
Yeah, where do they break down?
Exactly. And our goal is to figure out, like, at what point might these models actually lead to, like, a surface-level understanding
Right.
instead of a really deep grasp of the math?
Okay, I'm ready. Let's do it.
All right, let's unpack this thing. So let's start with those red and black chips
Okay.
and the mystery of integer subtraction.
Okay, sounds good. So the chip model, it's a super common way to teach about integers and operations with integers.
Right.
And usually you've got these two different colored chips. Like maybe you say, okay, black is going to be for our positive numbers.
Red is going to be for our negative numbers.
Got it.
And so the idea is that adding is kind of like putting groups of chips together.
Okay.
And then subtracting is like taking them away.
Okay, I see where this is going.
Yeah, so it's very visual, right?
Yeah, you can see why it's appealing.
Totally.
Yeah.
So like if you're doing 5 plus 3, you just get 5 black chips, put down 3 more black chips, and what have you got?
8 black chips.
8 black chips. There you go.
Which is 8.
Boom.
Exactly. It's like a direct representation of adding. Same deal with negatives. So like -5 plus -3. It's like, okay, we got 5 red chips,
Right.
3 more red chips.
8 red chips.
8 red chips, -8.
Perfect.
Easy peasy.
And it even works with subtraction, too.
Oh, yeah, for sure.
Wow.
So like 5 minus 3, start with your 5 black chips, take away 3 of them.
You got 2 left.
2 black chips left
Equals 2.
equals 2. Same thing with -5 minus -3.
Okay.
We start with 5 red chips and we take away 3.
2 red chips. 2 red chips, -2.
Perfect.
So in all these cases, it's like the number of chips and the color that's left that tells you the answer.
Yeah, so far so good. But I'm already thinking, like, what happens when we run into trickier situations?
Oh, yeah. Like what?
Like, say we're adding numbers that have different signs.
Right. Yeah.
Like 5 plus -3.
Right.
Now you've got 5 black chips and 3 red chips.
Uh-huh.
If we just go by the total number of chips, that's 8.
Right.
But we know that's not the right answer.
Yeah, the answer should be 2.
Exactly. So how does the chip model handle this?
Okay, so this is where you got to make the first kind of tweak to the model.
Okay.
You need to introduce this idea of a 0 pair.
Okay.
And the rule is that 1 black chip and 1 red chip together They like cancel each other out.
They represent 0.
Exactly. They represent 0. Now, this isn't like something that's just like built into the chips themselves.
Right.
It's not like how in chess, the different pieces move in different ways.
Yeah.
This is a rule that we got to like impose on the model
Right.
to make it match what we know is true in math.
Right. That 1 plus -1 equals 0.
Exactly.
Yeah.
So in the example of 5 plus -3, you get your 5 black and your 3 red.
Right.
3 of those on each side, they can make 0 pairs.
Right.
Poof, they disappear.
Yeah.
What are you left with?
2 black chips.
2 black chips, which is 2.
Okay, that makes sense. But it feels kind of arbitrary, doesn't it?
What do you mean?
Like, we're just saying these chips have this rule. It's not like something they naturally do.
Right.
Could that be a problem with the model?
That's a really good observation.
Mm-hmm.
And it kind of points to a bigger idea, which is that all math models are representations.
Okay.
And sometimes we have to add like extra layers of interpretation
Right.
to make them match the abstract concept.
Okay.
So the 0 pair is like one example of that.
Got it.
Okay, but now let's get to where the chip model for subtraction really starts to struggle.
All right. This is the breaking point.
This is the breaking point. Think about a problem like 3 minus 5.
Okay.
You got your 3 black chips.
Uh-huh.
How do you physically take away 5 black chips when you only got 3?
Yeah. This is where I remember things getting really confusing when I was learning this.
Right.
You can't take away more than you have. So what do you do?
All right, so this is where we get to the second tweak, and it's even more significant than the first one. It's called regrouping or renaming.
Okay.
So in the case of 3 minus 5, we got to get some more black chips into our starting set.
Right, but without changing the value.
Exactly. That's the key.
Oh.
So how do we do it?
I don't remember.
0 pairs.
Ah, okay.
We bring back our 0 pair so we can rename the number 3 as what?
5 plus -2.
Exactly. 5 black chips and 2 red chips. Because remember, the 2 red chips are negative.
Right. And that still equals 3.
It still equals +3.
Okay.
Now you've got 5 black chips, so you can physically take away the 5 that the problem is asking for.
And that leaves you with,
2 red chips.
which is -2.
-2, which is the answer.
Okay, so it works, but we're basically doing some kind of magic trick here
Yeah.
to make it work. And this is where the source really starts to question the model. They say that this renaming, it's not connected to like fundamental math concepts.
Yeah.
The same way that like regrouping is a normal subtraction with big numbers.
Give me an example.
Like if you have 14 minus 9 and you need to borrow,
Right.
you're reinforcing the idea of place value,
Right.
that a 10 can be broken down into 10 ones.
Exactly. It's like a deeper concept.
Right, but with the chip model, it's more like just a procedure
It's a trick
to make the model give you the right answer.
to make it fit.
Right, the math of saying 3 is the same as 5 plus -2 is fine.
Here.
But does it help us understand why 3 minus 5 equals -2?
Yeah, that's the question.
Yeah, it's more like a trick within the model itself.
Exactly.
And here's another thing that I thought was really interesting. They said that this renaming thing, it often needs you to already understand the concept.
What do you mean?
Like, if you already know that 3 can be written as 5 plus -2,
Uh-huh.
do you really need those chips to figure out 3 minus 5?
Right? It's like you already know the answer.
Yeah, it feels like you need to know the answer to make the model work.
That's a huge point. And that's like a big sign that the model is breaking down.
It's breaking.
The model starts to fail right at the place where students struggle the most.
With the concept.
With the concept, exactly. Like when they can't just, take away chips because there aren't enough.
Right.
So the adaptation that we made, it lets you use the model,
Mm-hmm.
but it doesn't really help you understand the concept any better.
Right. It might even make it more confusing.
Exactly.
So with the chips, it starts off as a really easy way to see what's happening with integer operations.
Right.
But then we need these adaptations,
Yeah.
especially this renaming thing.
Yeah,
And it feels like that's the breaking point.
totally.
At that point, the model might not be helping us anymore.
It might even be hurting.
Okay, so let's switch gears now and look at fractions.
Okay.
And we'll talk about the area model for addition.
Sounds good.
So the area model is another really common visual
Oh, for sure.
for working with fractions. And it usually looks like a rectangle that represents the whole. And then you divide that rectangle into equal parts.
Mm-hmm.
And you color in some of those parts to show the fraction.
Yep. And that's a really good way to show that basic, like, part-whole relationship of a fraction.
Right. You can instantly see that Like 1/4 means 1 out of 4 equal pieces is shaded.
Exactly.
And then people extend this model to show how to add fractions.
Right. You might have one rectangle showing a half shaded and another one showing a fourth shaded.
Right.
And then you try to think about like putting those shaded parts together.
Exactly. But the research that we're looking at, it actually points out that students often make mistakes
Oh, really?
when they first start using this model.
Like what kind of mistakes?
Well, like they might try to add 2 area models together where the holes aren't the same size.
Oh, so like one rectangle is bigger than the other?
Exactly. Or
Right.
they might try to combine models where the parts in each hole are different sizes.
Okay, so like one is cut into halves
Right.
and the other is cut into thirds.
Exactly. And they try to just put them together without making any changes.
Okay, yeah, that makes sense.
It's like trying to add a slice from a small pizza
Yeah.
to half of a large pizza
Right.
without considering that the pizzas are different sizes.
Yeah, you got to be talking about the same hole.
Exactly. So for this model to work correctly, there are 2 really important things.
Okay.
First, the holes have to be consistent.
So all the rectangles have to be the same size?
Exactly.
Okay.
And second, the parts within each hole have to be the same size.
Right.
You can't just add like halves and fourths unless you can make them have the same size pieces.
Okay, and that's where partitioning comes in.
Exactly. So
Yeah.
like if we want to add 1/2 and 1/4 using this model, we might start by taking the rectangle that's showing 1/2
Mm-hmm.
and cutting each of those halves into 2 smaller pieces.
Okay.
Now you've got 4 equal parts and 2 are shaded.
Which is the same as 2/4,
Right. And now you can put that together with the 1/4 rectangle.
which already has 4 parts.
Exactly. And now you can clearly see that you have 3/4 shaded in total.
Okay, yeah, that's a nice straightforward example.
Right. But what happens when you're trying to add fractions that have denominators that are harder to work with?
Yeah, like what?
Like, say, 1/4 plus 1/6.
Okay, now it gets trickier.
Now you've got to figure out how to cut up both of your rectangles so they end up with the same number of equal-sized pieces.
So we got to find a way to show both fractions with the same size parts.
Right. And in math, we know that means finding a common denominator.
Exactly. So like the research shows this example
Okay.
where the 1/4 rectangle, you can cut each of those fourths into 3 smaller pieces.
Okay.
So now it's showing 3/12.
Right.
And the 1/6 rectangle, you can cut each of those 6 in half,
Okay.
and that gives you 2/12.
Gotcha.
And then you can put those together, and you can see you've got 5/12.
Okay, so to make the model work for fractions like 1/4 and 1/6,
Yeah.
you have to do some thinking outside of the model.
Right.
Like the model doesn't tell you that you need to find a common denominator of 12,
Yeah.
and it doesn't tell you how to get there.
You kind of got to figure that out on your own.
Right, and it gets even more complicated when you add in fractions that are bigger than 1.
Oh, yeah, for sure. Like, what if you had 1 and 1/2 plus 1/4?
Exactly. Now you need a bunch of rectangles just to show the whole number and the fraction part.
Right.
And you still got to make sure all the holes are the same size.
Uh-huh.
And then you got to cut up all the fraction parts to make sure they're the same size too.
Yeah.
And then you can finally combine them all.
It's a lot of steps.
It is.
Yeah.
And this is where the source really starts to point to the breaking point of the area model.
Okay, so it's getting too
Okay, so-
complicated.
yeah.
Yeah, for a few reasons.
Okay,
Right.
tell me more. Well, first, like we were just talking about, you have to do so much work outside of the model
Right.
just to make it usable.
Yeah, like figuring out how to partition those rectangles.
Especially when the denominators are tricky.
Yeah.
It's almost like the model relies on you understanding the symbolic math already.
Which is what it's supposed to be helping you with.
Exactly. Like you might need to calculate the least common multiple of the denominators on paper
Uh-uh.
before you can even draw the rectangles.
Yeah, the model doesn't lead you there.
Nope.
You got to know it already.
And second, when you're working with those fractions that are bigger than 1,
Right.
it's just so much work to draw everything and cut it all up.
Yeah.
You can get so caught up in the steps that you forget about the actual concepts.
Like
Why do we need a common denominator?
yeah.
It's almost like the model becomes more about getting the drawing right.
Instead of understanding the math.
Exactly. And when that happens, it might actually be hurting your understanding.
Right. Getting in the way.
So it feels like it's gotten so complicated that it's actually harder than just adding the fractions the normal way.
With pencil and paper.
Right. Like if you're using more brain power to get the drawing right
Yeah.
than to actually understand the math,
Then what's the point?
right, it's lost its value at that point.
It's broken.
So we've seen this with both the chip model and the area model.
Yeah.
These visuals, they start out helpful, But then they get to a point where they're not so useful anymore.
They break.
And it happens when we need to make changes that hide the math,
Right.
or when the model itself becomes harder than the math it's supposed to be showing.
Totally.
So what does this all mean for us as learners?
Well, the big idea is that every model in math,
Every single one.
even the ones that seem really intuitive, they all have these limitations,
These breaking points.
these breaking points. And realizing that that's not a bad thing,
Okay.
it actually helps us understand the model better.
How so?
It helps us see what it's good at
Okay.
and what it's not good at.
And that helps us understand the math better.
Exactly.
And for our listeners, you guys are all about learning things quickly and having those aha moments.
Right.
I think figuring out when a model breaks down, that is an aha moment.
Totally.
It shows you the limits of one way of thinking about a problem.
Right.
And it makes you find a deeper, more abstract understanding.
It pushes you further.
And, if you've ever felt overwhelmed by all the math stuff out there,
I think we've all been there.
like all the different concepts and all the different ways to learn them,
For sure.
knowing that these models have limits
Yeah.
can actually be kind of comforting.
How so?
Well, it means you don't need to force a model to work when it's not working.
You can let it go.
Right. You can say, okay, you were useful for a while,
Yeah.
but now I need to use a different tool.
Exactly.
And this research suggests that the best thing about models is that they make those abstract ideas more tangible. And they can even help us figure out those standard procedures.
Oh, interesting.
Like if you're working with a model, you might start to see patterns
Right.
that lead you to the rules of arithmetic or algebra.
Okay, that makes sense.
But it's really important to pay attention to the changes that you make to a model
Okay.
and make sure that they're still connected to the math ideas.
Right, not just like tricks to make it work.
Exactly, because if they're just tricks,
Uh-huh.
that might be a sign that the model is breaking.
Gotcha.
And one more thing that I thought was really interesting.
Yeah.
The research pointed out that even when people come up with alternative models
Uh-huh.
that seem more intuitive,
Right.
they're still going to have breaking points.
Oh, interesting.
Like they gave the example of using debt and credit to think about integers.
Okay. Yeah.
That works in a lot of cases.
Right.
But then what happens when you try to think about taking away more debt than someone actually has?
Right. That doesn't really make sense in the real world.
Exactly. So even those models that are based on real life,
They still break down eventually.
they do.
Interesting.
So the point isn't to never use models.
Right.
It's that the process of figuring out where they break
Uh-huh.
is really helpful for learning.
Okay, I like that.
Yeah.
So it's all about being critical of the tools that we're using
Exactly.
and understanding how they connect to the concepts.
Right. So for all of you learners out there, how can you tell if a model is breaking down?
Yeah, that's a good question.
Well, the research gives us a few clues.
Okay.
One is if you're always having to make big changes to the model
Uh-huh.
to make it fit new kinds of problems.
Okay.
Another is if it feels like you're just using it to calculate the answer
Right.
instead of to understand the concept.
Okay.
And finally, if using the model is actually harder than just doing the math without it.
Yeah,
That's a big red flag.
makes sense.
So to sum it all up, these models are really important for learning math.
Definitely.
They give us a way to see and sometimes even touch those abstract ideas.
Huh.
But as we've seen today, they all have limitations.
They'll break eventually.
And figuring out where they break,
Yeah.
that's what helps us really understand the math behind them.
That's a good way to put it.
And the goal isn't to be afraid of models.
Yeah.
It's to use them strategically.
Right.
And to pay attention to when they're not working anymore.
And when that happens, it's an opportunity to learn.
Exactly. So here's something for you to think about. We've talked about the chip model and the area model.
Right.
But what about other visuals or analogies that you've used in your learning?
Yeah.
It could be in math or in any other subject.
Good point.
Think about where they might break down
Yeah.
and what that tells you about the concept they're trying to explain.
Yeah, that's a good challenge for our listeners.
It is. And often it's when we push those boundaries
Uh-huh.
that we really start to understand something new.
I like that.
We hope this deep dive has given you a new way of looking at these familiar learning tools
Yeah.
and at the fascinating ways that we learn.
It's been fun talking about this.
Me too.